first speaker is Anna-Lena, and we'll just get right into it. Thank you. Welcome, Anna-Lena.
Yeah, thank you. Nice you're all here after the party yesterday. I want today speak a bit about building trust, use cases and implementations of TPM 2.0 in embedded Linux systems. Why this talk? I had in the past, I think, around 2 years, several use cases and projects with TPM in there. And I learned that there's so much more to know about TPM and so much more deep dive. And a lot of people know there is a TPM, but what it actually is and how you can use it is not that spread. So I'm here to spread the word. I'm Anna. I'm an embedded systems engineer from Germany. I have a background in embedded systems, electrical engineering. I basically started my embedded career with embedded Android, and nowadays mostly focusing on Yocto. And now let's start with a bit 101 about TPM 2.0 and start with what is TPM. Basically, it's a trusted platform module as specified by the Trusted Computing Group, the TCG. And this definition or standard from them also made it to ISO IEC standard. Mostly if you think about TPM, it's referred as a cryptographic coprocessor, as a hardware security module, a hardware root of trust. Often the word hardware is called when thinking about TPM, but basically that's just part of the truth, because there is different ways to implement TPM. There are discrete TPM hardware implementations, but there are also integrated TPMs integrated in software, as they are used for the Intel platform trust technology, or when thinking about ARM in or area, it's most often firmware TPMs that are implemented in trust zone and used, for example, in smartphone applications a lot. But there are also software implementations for testing or hypervisor and all that stuff. So it's not always real hardware, with some pros and cons that are coming from that. So when you think about TPM, you can picture it a bit like that. It's a device providing cryptographic coprocessor functionality with random number generator, key generator, hash functions, and a ton of algorithms, with some permanent memory storing some seeds, templates for key generation, slots for storing keys persistently, the platform configuration registers, something we will speak about later a bit in detail, and a lot of seeds, and also providing some volatile memory for handling active session keys and non-persistent data. And if you think about the capabilities of your TPM on your device, for example, you can just check it with TPM2 getcap command, which is part of the TPM2 tools software set. That's just an example how you can find out a bit more what is actually available in your platform. And when speaking about software and software implementations, let's dive into the software stack for a minute. The software implementation, the library, and the stack is also defined by the Trusted Computing Group. And it's defined as a stack you can see in there. There are basically 3 API levels in different I don't get a word right now. In different abstraction levels. There's a system API, basically mapping on the low-level TPM commands, an enhanced API and a feature API for more sophisticated use cases. In applications, there's a TPM command transmission interface, TCTI, which you can think of as a kind of hardware abstraction layer for TPMs, and a bit of functionality on the lower level, TPM access broker, resource manager, device driver, and how they implemented, if they're implemented as one thing or if they're even implemented is a bit up to the use case. And yeah, basically there are several implementations for the TPM software stack. There's a reference implementation done by Microsoft, a Microsoft implementation itself. But when working with Linux, it's mostly the TPM 2 TSS implementation you will use. And I think it's quite good quality and proven software. So that's basically the thing that will be there most often if you're not in the Zephyr world, for example, or the microcontroller world. And I brought some really wild picture from the TPM2 software GitHub page. The GitHub page or organization also implementing the TPM2 TSS software stack. It's a bit wild. I don't know if you really see it from your perspective right now, but what I like from this picture is it clearly shows the HAL functionality of the TCTI implementations. There's a UEFI implementation, for example, simulator implementation, and several for the device in Linux. And it also makes clear that there are 2 TPM driver implementations and devices available in Linux, one with a resource manager available and one without. And yeah, let's continue with a bit more about TPM terms. Speaking of keys, I will speak mostly about the asymmetric keys because they're the most used in most use cases, but generally the most thing I say is valid for the symmetric ones as well. There are several algorithms available on the TPM, mostly ECC and RSA. You can generate primary keys, so-called primary keys, with the TPM based on a hopefully hardware-based random number generator. You can also import external keys, public and private. You can use the keys for the usual key functionality stuff for encrypting, for decrypting, for signing, attestation tasks. And the one nice thing about TPM is the thing with primary keys and child keys. Primary keys are really part of the TPM. They're derived from a seed, the cryptographic root. And the primary keys, the private part of them, never can be extracted from the TPM. You can directly use primary keys, but it's more common to derive child keys from primary keys. And they can leave the TPM because they use a mechanism called key wrapping, which basically encrypts the child keys with the primary key. so they cannot be used at all without exactly that TPM, and make it safe and secure to store the keys outside. And speaking about key hierarchies, I showed one hierarchy, but there are indeed 4 hierarchy levels and hierarchy roots on TPMs. The endorsement hierarchy, which is controlled by the TPM manufacturer, also called privacy owner, which is intended for privacy-sensitive data, for validating the authenticity of the TPM, but it's also a bit of privacy concern, because with that hierarchy and that seed, you can really track down keys to exactly one TPM. There's a platform hierarchy, a platform seed, which is used for the platform manufacturer, the OEM, for basically that instance that ships and controls the early boot code, like UEFI for secure boot, for example. There's an owner hierarchy that is basically the default one used if you work with the TPM from a user perspective on your own laptop. And there's a special one, the null hierarchy. This has no persistent seed. It's get a random seed from the random number generator each time you power cycle the TPM. And that's used, for example, for sessions. Sessions are something like, how's it called, a secured, what is the word? I don't remember. A secured set of operations bundled together that are encrypted, so all your TPM operations done in one session are encrypted with, for example, HMAC, using the seed from this null hierarchy. And generally, seeds act as the cryptographic root of the hierarchy. Keys based on the seeds can always be regenerated. And yeah, I think that's it for key hierarchies. And the next thing I want to talk about are the platform configuration registers. I think that's the most unique part of TPM, and I think also the most powerful. Platform configuration registers are 24 or more dedicated hardware-based registers holding a hash. You can see with the TPM2 getcap PCR commands what hash is used on your device. SHA-1 is basically for compatibility use cases. I think it's not used in TPM2 anymore at all. And the platform configuration registers are used to cryptographically measure and record software states. This can be done only with really strict conditions. For example, the most of the PCRs can only be set or reset on system boot power on, and on a really specific TPM locality level, which is a bit the same or similar concept as CPU run levels, the rings, the CPU rings. And one really interesting thing with the PCRs, it's they are not written once, but extended. So every state measured with one of the registers extends the already existing value in there. So if the the ordering of the operation changes, the resulting hash also change, and the value is not the same anymore. You can detect this and use this to measure the integrity of your system and act and react. There are a lot of these registers. I think not all are used right now. The most interesting are the first, I think, 41, and one that's specifically interesting for use, for example, also for encrypting data, is the number 7, which measures the secure boot state. And I've a use case for that later in the presentation, where it can be used to encrypt a data partition as long as the secure boot is in place and correct. About a locality, there are 4 levels, 5 levels. The 0 level is basically the static root of that. In this level, directly if the system starts, the PCRs can be resetted, and the hash in the numbers 0 to 7 can be extended, and the operating system, Linux, runs in the locality level 4. So Linux would be able to modify the value, for example, for secure boot or all that early components. If you want to have a look on your PCRs on your platform, there are several commands to do that. Systemd analyze, for example, or TPM 2 PCR read. And you can also try it out and check. The values shouldn't change normally between reboots. So even if you do an update, for example, the secure boot state must be the same. So yeah, short recap. We learned about how TPM looks like and about some of the major components and concepts in there. So let's go further with the question, how can we trust a TPM? Because here there are a lot of components and steps in the chain. You need to trust the manufacturer of a TPM, the manufacturing process, your system manufacturing process. You need to be sure no one interjects your PCB and sniffs something on the PCB. You need to trust a boot code and provisioning process. And in general, the most of them is not a cryptographic issue. It's rather an issue of trusting the process, controlling the process. And so it's not really solvable only with tech, but a really big issue in trusting your platform. But what you can do at least is verify a TPM's authenticity using the endorsement hierarchy, for example. As said, this hierarchy is controlled by the TPM manufacturer. And the primary keys in this hierarchy are really constrained to one specific TPM. And with that, you can verify it's authentic. You can really identify that machine. So if there are keys generated with this endorsement hierarchy, you can track it down. They're really were generated by that machine, which is also a bit of privacy concern, depending on your use case. And yeah, the endorsement key and key pair can be generated and regenerated using the seed and a specific key generation template. And there's also endorsement key certificate, which gets in there during the manufacturing step. So you can use both of that to validate it's authentic by first using the hierarchy level on the TPM to generate the key pair, read the public key, obtain the certificate, and then you go to your TPM vendor website. You should know which vendor and which model you have or you expect on your platform. And then you can do 2 steps. First, you can extract the public key and validate it matches the one in the e-key certificate. You extract also from the TPM to make sure your TPM itself is valid and not tampered as a platform. And in the second step, you can use the root or intermediate certificate or both you get from your vendor to verify the certificate and the public key is valid for that platform, and you really have the TPM you expect as part of your product. And yeah, last, some practical examples from some use cases I implemented with Yocto, for example. When you want to integrate TPM with Yocto, there are basically 2 layers providing the TPM functionality, Meta Security and Meta Secure Core. Basically, both do the same. If I would be asked, I would basically prefer a bit the Meta Security layer. I think it's a bit better from the quality and the maintenance. But depending on your use case, you can also mix and match what is needed. And the first use case I want to tell a bit about is establishing a chain of trust by implementing Secure Boot on an Intel platform with Meta Secure Core, Meta EFI Secure Boot, and Manda as an update client in place. The idea with that is a bit of ensuring your device runs a trusted, signed, and untampered bootloader, kernel, and whatever of binary blocks you want to validate in the first step. And it's about establishing a trusted environment for later application use for critical tasks. For example, to make sure only a trusted device with trusted software can access a cloud platform. And for that, you can also detect if Secure Boot is disabled during runtime and make sure only trusted platforms really can access your IP. And one thing about ARM platforms, maybe on ARM, you rather use some special storage on the device that can be burned with fuses to deploy your secure or verified boot certificates instead of the TPM. That's also a valid use case, a bit of another way to build up this initial root of trust, but also a valid use case, just another mechanism. And yeah, if you implement something with UEFI on Intel, it looks a bit like that. You boot into UEFI with Secure Boot enabled. Your bootloader, your first stage bootloader does check, are the certificates in place, checks the certificates with the TPM, and depending on the check, it either boots up or shows you a red blinking error screen telling you the certificates don't match, and yeah, you can't use the platform like that anymore. And about the implementation a bit, last time I really tested it was with Crockstone. Uses, as told, meta-EFI secure boot, which provides you already a lot of tools. Group EFI implementation, EFI tools, mock utils, shim, whatever. It provides also patches for grub, signing tasks in Yocto for kernel bootloader and all that stuff. And already it does the integration with TPM for storing keys, certificates, and looking them up in there. And also provides a grub entry that does the initial certificate provisioning step with TPM at booting up. One thing about that layer is it's mostly described for the use within a DRAMFS. When booting up with Yocto and Manda as an update client, I don't want to have in a DRAMFS. I think Manda is also not really aware of using in a DRAMFS at all. And also I don't want to have that complexity level in there. So there are a bit of tasks needed to get that done without an inner DRAMFS that are not that much documented. And Manda is also not aware of using a boot partition, an EFI boot partition distinct from the root FS. So you need some extra steps to update the kernels in there. But Manda with state scripts are perfectly prepared to do this task. It's just an extra step to implement. And basically from a Yocto perspective, it's rather simple if you once figured out how to do it. It's integrating the right tools and commands in there. You need to provision the signatures for the kernel images and the bootloader in the boot partition. There's also one trick when using Manda. They process the image boot files variable on their own afterwards and have some issues with multi-line parsing. So it's needed to write all the things you need to want to append to the image boot files in one line to make it happen. Otherwise, the whole thing will crash. And then one important step is also checking the crypt configuration to make sure the search path is correct. And afterwards, everything should boot up with secure boot enabled on this Intel example. And with secure boot in place, you can, for example, make use of the PCRs, especially of the PCR number 7, the secure boot state, for encrypting user data. When having embedded devices in field, I think you all know the situation. They're mostly unattended. You don't have a user in place that can type in a password to encrypt a partition. You also want to have really strong security per device in place. And the basic idea of this use case is utilizing the TPM PCR7, the secure boot one, or maybe even 0 to 7 or whatever, to measure the system state and make sure you run a trusted kernel in a trusted state, trusted software, and bind then the encryption task to this software state. So you don't need to have any user interaction, but still have a strong encryption in there. And if the device got tampered, for example, if the PCR state changes, or if secure boot is disabled, it's not possible anymore to unlock the partition. So example, for a person wants to use your device in another context, wants to disable secure boot, that's perfectly fine from that use case. The data, the privacy relevant data is locked. So here it can't be used in the initial context anymore, but that's fine. And to implement this, one possible way is utilizing systemd and looks and crypt setup, for example. As you want really specific encryption for a device, I think it's easier to integrate it, the encryption part, in the initial boot up step. So you can utilize a systemd service that starts right before the partition.mount step, and then run a script utilizing crypt setup for writing looks headers in the first step and encrypting the partition afterwards. It's split into two parts because of encrypting an existing partition. And afterwards, after this initial encryption is done, you can bind the TPM PCR to your encrypted partition using, for example, systemd crypt enroll, which is basically just a wrapper around the pure TPM commands, which make it a bit easier to do it correctly and secure. And from a Yocto perspective, it's as well not that complicated. You need to enable some package config for crypt setup as well as for systemd. When running on Kirkstone, I think it's valid to speak about Kirkstone right now because it's still active and still supported. You also need to make sure some library implementations are correctly written to your device. There was a bug back in days which does not deploy some of the libraries. So this extra step was needed in there. With scarfgap, for example, that's fixed. And then you can write a script as seen here on the right, for example, really a basic example which uses a randomly generated one-time password for doing the encryption in the first place. This password can, for example, be saved afterwards to cloud to make sure you as a system manufacturer can restore the data if something happens to the system, but it can also be just deleted and do whatever you want with that. But yeah, after this initial encryption step, the magic happens with the command down right there, systemd crypt enroll, which binds the partition, the looks partition, to the TPM PCR number 7, utilizing the capability of looks encrypted devices to have several keys deployed for one encrypted partition. And to open up the device without user interaction, you can, for example, utilize a crypt tab entry, also referencing to the TPM PCR register. A crypt tab entry is utilizes the systemd crypt setup generator, which generates on runtime a task for encrypting that partition when the device boots up. And then you can just use the mapper device in the F-step entry. One hint also when using Mender as a client. Mender also modifies the F-step in the rootfs post-process command, so it's really needed to make sure the ordering of your operations is in the correct order to get the FS tab really written. And yeah, as the time becomes a bit limited, no more really use cases, but more ideas how to utilize TPM. For example, you can make more use of the Linux integrity measurement architecture, maybe also together with the Keylime project. You can store sensitive counters, read-only information or whatever in non-volatile RAM of the TPM. Or you can use TPM back keys for SSH, SSL, your application use or whatever. Or maybe your software stack already utilizes the TPM without you already knowing, which is the place for example, Azure IoT Edge. And yeah, let's recap. When using TPM devices, it can help you with cryptographic operations, random number generation, with trusting kernels and your boot infrastructure. It can measure the system state and help you with integrity issues. You can store tamper-resistant information in the non-volatile RAM, and a lot of more use cases. Just get creative with the possibilities in there. But on the downside, TPMs are there, they're well supported, they're affordable, but when building up an embedded system, it's always an active decision to really take it in, really utilize it, maybe pay the additional cost for integrating one, or the additional cost for integrating a firmware one, and really use it, and really use it good and well. It's not a non-brainer task. There are still attacks on the TPM. For example, if you use a discrete one, there are sniffing attacks on the I2C or SPI bus. It's a thing about who owns and controls the platform. Think not so much for embedded devices down the field that are not really used as a computer, but as the device built with and around the computer. Maybe it's a bit of privacy concern of using TPM if the keys and key infrastructure is trackable down to one TPM. And one of the major points, you really need to trust the vendor, the device manufacturer, the PCB manufacturer, and the whole process. And this task, I think, cannot be solved really on a technical level. That's more process thing. And yeah, I think that is. Thank you for your time. Questions?
You touched on this a bit, but do you have any recommendations for when you have a hardware platform where you cannot retrofit a hardware module? For example, AMD EPYC servers, and then you are forced to use the AMD FTPM. Do you have any recommendations when you find yourself in such a situation, what you should do to get more trust in what you get?
That's a good question. Basically, I would try to find out what TPM should be in place and really validate it's the one that should be there. You maybe can also wire up an external TPM. But yeah, this trusting issue is really one of the main pain points in using a TPM.
Yeah, because our UEFI vendor offered to provide source for a significant amount of money, but source is only part of the way there, because then you need to verify that they do everything correctly. In the end, we went, like you said, with an external TPM, but I was curious if anyone actually is using firmware TPMs and is happy with them, because it seems like a huge risk, like a checkbox thing, like, oh, we have a TPM, but not really.
Yeah, I think firmware TPMs also have some pro points, because with this integrating directly on the chip, there's no attack vector like SPI or I2C bus sniffing, but it's always that, this, which one of the risks do you want to have?
Okay, thank you.
Thanks for the talk. Regarding containers, do you have any status on support for and accessing TPM through containers and sharing keys and so on? Any information on that?
Let me think about it. I never tried it on my own, but I think it's definitely possible to access TPM from containers. Maybe you can also use software TPMs for hypervisors, for example, but sharing the resource has also some risks. So this trusting matter is still an issue.
Hey, I wanted to ask about the PCRs. So when you power off your machine and power it on again, do the PCRs in the TPM survive, or is their state regenerated every boot?
They are regenerated at each boot. So it's really needed when they're regenerated, the same ordering happens to receive exactly the same value in the register. And that's basically the point of measuring the integrity. If they would survive in there, the whole trick of that won't be working.
Thank you.
So continuing to the PCR questions, a use case that I often meet is that if we want to include GPL3 in the firmware, we cannot really use secure boot, because that would not allow the user of the device or the owner of the device to actually flash new firmware, modified firmware at least. So instead we want to use measured boot only, and then unlock the data partition only if we boot something that we trust.
Yeah.
But how does that work with an A/B update scheme? Can you have like multiple hashes bound, PCR hashes bound to a device, encrypted device, so that you can actually update the other partition and say this is also a valid boot sequence?
Yes, that should work. You can basically use several key slots for LUKS encrypted devices, I think around 7, if I'm right. And you can basically use any PCR you want. 7 is the most common used, the secure boot state. But in fact, it will work with everything that really has a predictable value and will not change the value over time.
Okay, thank you.
One more question.
great talk. I've enjoyed it. Thank you very much. So one of the things that I was facing is a problem. Actually, I mentioned it with a private conversation yesterday at the party with Anna-Lena. It's on boards like Raspberry Pi, where you don't have a built-in TPM, one of the options is to attach a TPM 2.0 over SPI, but obviously there are some risks involved due to the option for men in the middle of attack, someone to listen to the communication going on the SPI bus. Obviously, there is probably not a perfect solution, but what are the best practices to avoid this or to minimize the risks?
That's really a good question, and one of the important ones when working with TPM. I think one possibility would be really checking the TPM device is the one expected, the way I showed, for example, or make the whole hardware inaccessible. That's not a really good solution. But yeah, basically that are the really hard questions when working with TPM. It's not really about the implementation. It's not about the cryptographic tasks. It's really about securing that process steps and make sure this path is not tampered on a physical level.
Thank you very much.
Okay, thank you. Very good.